Excellent. So I have a draft of the group project I want everyone to work on in regards to the shell application. So I'm going to finalize that later tonight and finally give the specifications for that to you all formally so you can actually start working on that project. And then I'll figure out what due date I want to put onto that as well. Uh, the parameters are going to be similar to what I had stated earlier. Effectively, I'm going to give you a list of various shell applications, command line tools to select from, but you will not be limited to those tools. These are just the ones that are very common and popular and sophisticated and complex enough that I think it would warrant having a small student group be able to play around and give a demo, probably about a 10-minute demo or so of that particular tool to the rest of the class. And then we could all come away having experienced a vast assortment of shell line tools from a consequence of that. Now, if there is a tool that you've used in the past or that you're interested in using that's on the list, you can go ahead and just seek permission to use something that's not on the list. Now, each group will have to present on a unique tool, though. So once you've so when you choose one that you're interested in, you want to go ahead and make it your own as quickly as possible, right? So another group can't claim access. And it seems like the fair rules for that is once you've assessed, you can start to consider who your teammates are. When I give you the document, I'm just going to use post request inside of the Discord for priority in terms of who gets what tools. So when you go to make a claim, go ahead and make your claim, make sure no one above you had already made the claim. And if you did, then make a better claim. Now, this does beg the question though. Does Discord allow you to edit your post? Oh.
Yeah, it says edit.
Okay, so you have to make the claim and that post can't be edited. Nope. So that's how we'll solve that problem. Excellent. And I think this will be the last day that we do kind of like the more formal kind of lecture presentation with slides. I want to finish up this slide deck that I have here, and then we're going to migrate. I'm going to launch the Bomb Lab, and then we'll start playing with the Bomb Lab in class itself. And so I finally got done my submission process. So for the rest of the week, after I get a little bit of ability to recollect myself, I'll be able to go ahead and address all of the questions that have piled up, I'm sure, inside of my Discord message box. Okay. With that said, does anyone also have any other questions before we start on the PowerPoint presentation on chapter 3, where we continually examine the role of machine code in driving our underlying systems? Check online. Perfect. Okay. Yeah, so I guess to bring us back to the through thread of where we last left off, on Monday, we're trying to really motivate what is the value of machine code and by consequence assembly code after learning how to take that class in assembly. Like, what is the overall picture that plays into computer systems? And so we started with a very topmost approach, where if you think of the top as being very abstract, and we're slowly kind of building our way down to explain the actual interoperational components of our computer systems. Once we understand that theoretically we can represent anything in our system as binary vectors, then one of the major roles that the system then has to do, the actual hardware has to go ahead and support, is not only storing the representations in something that's a physical representation, physical realization, but then being able to bus those representations around where they need to go so that we can do meaningful operations. And we've defined all the meaningful operations in terms of these operators that can actually be modeled using logic gates, which can be modeled with real world processes. So we can actually create real world physical constructs that then implement the logic gates, which allows us to transform one representation into another. So we've covered that. And so now what we're looking at is we had looked at the instruction set that's defined by the processor, which is really designed to go ahead and facilitate the operations and the access of our binary representation. So now what we're going to start looking at is how the software is controlling the hardware to do the fundamental things that the next layer application is going to require on top of our system. So really, as we stated earlier, the very big drivers of what we need to occur at the very low levels is being able to move data around and then be able to create control structures for our instruction pointer, since everything is just so sequence sets of processing, how we can go ahead and model the idea of control logic there. And again, we'll go through this relatively briefly because I'm pretty confident you covered a lot of these concepts in assembly already. This lecture is really just to emphasize how this then maps, how all of that assembly learned then maps into the larger ecosystem that designs and develops and implements and realizes our computer system holistically. So I think we left off on this slide, right? The operand specifiers. So when we talk about our operators typically require operands. You can think of those as your parameters when we redefine an operator mathematically into something like a function in computer science. Functions can take in parameters, operators use operands. So the operand specifier is going to be what type of data can our operator take. When we're talking about the machine code aspect of data type, when we're talking about the assembly code, well, we looked at the data types in assembly code. Let's think about it more in terms of the machine code concept. Here, what we really care about in terms of types and the way that data really manifests itself at such a kind of abstract level where it's just binary representation is going to be, where does this representation reside at? So really, there's only three types of specifiers when we're looking at these operators that we care about. It's going to be the immediate, you can see on this list, immediate, the register, and the memory are going to be the types that we concern about. So what are the operands in particular for the operators we're going to look at that deals with our machine code, our assembly code representations? Well, it's going to specify typically a source value for the operation and a destination. So again, these are places to look for information and places to write your information into. So read and write operations. Everything's fundamentally going to then resolve to be one of these three concepts. So the immediate type of operand is really a constant value. So typically we would put a $ in front to specify, hey, this is a constant. Constant values are highly optimized by the system because they can just look them up. It's not something that is in memory, and it's not something that is in the register space. It is the idea of a primitive value in Java, drill that all the way down and understand that immediate values are just something we can do lookups of. Something that's provided to us by the system. It's important enough that there's a immediate representation of that. Okay, so that is one type of operand, which is effectively a type of data at this level. The next is going to be register. Registers represent the locations of inside of the CPU register space. So that's going to be where those contents are at. And so our registers can actually have various sizes. We can have, say, for instance, a 1 byte register, a 2-byte register, a 4, or an 8-byte register. We talked about that last class, and we talked about the evolution of these register spaces with the x86 architecture. And the last type is going to be a memory reference. Now, this is going to be based off of the effective address that that memory has that you can then read and write from our virtual memory addressing that we go ahead and have access to. So notice the big takeaway with these types are all really focused on where does the data live at inside of the system before we do an operation. So it's dealing fundamentally with the type of addressing where our data is located in our system, whether it's immediate, register, or memory. And so there's going to be implications for these operands on whether one of these types can be legally a source or legally a destination. Like clearly, an immediate type can always be a source, but it can never be a destination. You can't overwrite the value in an immediate address because it's designed to be immutable and constant. Whereas with registers and memory references, that's not true. Those are locations you're supposed to not only be able to read from, but also be able to write into. And so since we've mentioned these types as effectively as ways of reading into locations inside of our system to go ahead and access data or to then write data into, let's talk about some of the addressing modes that the system recognizes so that when you see this in code, or if you write code, you'll understand how this actually interacts with the underlying system. So the general form, by the way, that we can go ahead and do our addressing mode is here. Let's use, we'll have our immediate offset. So this would normally be some kind of integer value. I would replace with IMM. And then inside parentheses, you effectively have a tuple that has 3 values. The first is going to be your base register, the memory address you're starting at. The second is going to be the index register, the offset by how much spaces from the base you need to jump to. And the final amount is going to be our scale factor, which can either be the size of 1, 2, 4, 8, which is how big is the data type that's typically held in this memory location that we have to jump past to get to the next element in memory. It looks a lot like conceptually how we do indexing for arrays, but this is just how we do indexing for data in our addressable space generally, right? So if you're thinking about our addressable space as effectively just one giant table that we can insert binary representations, then the system's going to be able to allocate at any time whether it should be in like a one byte chunk or two byte chunks or 4 byte chunks, and then where does it start and how many elements if it is a more complex type that can have associated values. And so this formatting scheme, that's the general formatting scheme, supports any kind of way we need to go ahead and access locations inside of our system to be able to extract those binary representations. If you think about it, it's a very complex kind of filing problem. And again, the way that we can see this mathematically, I guess, would be this representation here, where it's our immediate plus the value in our base register plus the value in our index register. And then that index register has a multiplicative property that scales how many units you have to jump by. Okay. Let's talk now that we've talked a little bit about addressing modes, we talked a little bit about the different types of data in terms of addressable space. Now let's start talking about some of the fundamental calls we use inside of assembly to facilitate being able to get our code to run. We have our movement instructions. So let's just jump to that. Those are the very common ones. These are ones you probably opened up day 1 or day 2 in assembly. Here you have a move instruction. This allows you to, and does it give you this doesn't give you the operands. Okay, so anyway, we can usually append to the end of move, the amount of data we want to move. So move B does 1 byte, move W is 2 bytes for a word. Move L will do 32 bits, so that's 4 bytes. And finally, move quad word will be our 8 bytes. And so we had mentioned, based off of types, that you always have a source operand and a destination operand for these operators. So the source can be an immediate. So it can be a constant value, it could be a register, so some value in a register space or inside of memory. Now, the destination for moves can only be register or memory, right? We can only move data. Those are the 2 writable spaces for us. So you could think of sources as being read spaces, our destination as having writing privileges on them. Now, we do have the stipulation, you might recall this, that you cannot move data directly between 2 memory locations. You can read data or access 1 memory location, but you usually have to pair that with also operating on one of the register spaces, because our CPU has much more direct control and access to that can be kind of like the buffer zone in a way, a buffer memory to be able to store our data before we process and then send it somewhere else. So, and that's obviously something that you've already covered. So I will keep moving on. So let's look at just some quick examples of our moves to ensure that we all kind of understand what it looks like in practice. Here, I'm going to move L, so it's going to be able to move 4 bytes. And here that the source is going to be a constant value. We know it's a constant value because we prefix it with a $ symbol. And then the second is going to go ahead and be our register. We know it's a register space because we prefix it with the % symbol, EAX. So this would be a immediate to register operation. We're removing some sets of bits from our immediate space into our register space. And so here we're doing a similar thing. This represents a register to register, source to destination move. Here we're going to do another register. Well, here we're going to do actually memory. So one way we can go ahead and define memory is, remember the address mode we had just spoke about. We use in the address mode the sets of parentheses that serve as a tuple. This is the set of symbols we use to provide the context that this is the memory lookup. So here, RDI would effectively be, so the address in RDI would represent the base index, and the address at RCX then, our counter register would represent the index value. And since there is no scale factor, the default scale factor then would be 1 byte. And so here then, we would then move that into the register AL, the lower 8 bits of the RAX register. So that would be a memory to register by 1 byte move. Here's another representation of a constant value. So here, this is just representing, this is a hexadecimal value. Remember, if we prefix it with 0x, we know that that's hex versus just a decimal representation. This is just illustrating you can use either type for immediate. And then here, we're going to move this into memory. Again, whenever we use the parentheses around what looks kind of like a register space, that means we want to use that as a memory address and not as a value from the register space. So here, this would be immediate to memory for 1 byte. And then finally, this is a register lookup with just the %, not the parentheses. And then this is our, if you remember, our address mode. Inside the parentheses is going to be our base index. And then here, we're going to apply an immediate offset where effectively by doing -12, it's going to subtract 12 from that memory address. So this is a way to actually jump from using your memory address as a basis, being able to jump around. And so this would represent a register to memory. And so this would actually jump and then be able to overwrite past that jump when it's because that's a destination value that's doing there. Excellent. Is there any questions, or is this pretty familiar with everybody? You kind of covered the differences between immediates and registers and your memory lookups, and you're familiar with the notational. Like MASM is pretty consistent with what you did with MASM 32. Excellent. Okay, so just a quick additional note on move. You can also do move absolute quad, ABSQ, and this is just designed with dealing with 64-bit immediate data. Oops. So if you see that, just an example of the usage, suppose that you have this 64-bit representation, hexadecimal representation. This would be your destination constant value. And then this is going to be, this is going to be your source, the constant value. This is going to be your destination, this register. So this instruction would just simply move that 64-bit immediate value into the RAX register. Now, there are instances when you move data that you might want to go ahead and affect how that move fills or modifies the destination. So for instance, you have move Z and move S. Z will 0 extend the source value to fill your destination if there is any unwritten bits over the course of that move. Whereas move S will sign extend the source value to the destination value. And so clearly the decision on move Z or move S is predicated on whether you're using signed data or unsigned data, whether you want to zero fill or not. So an example of this is suppose, and usually this is important when you need that offset, when you're moving a smaller sized bit vector into a space that is a larger size bit vector, right? So in this instance, in this example, we're going to move the least significant 8 bits from RAX, right? Which we can access just using %AL. That's the lower half of the EAX or RAX register. And then we're going to move that into as our destination BX, which is going to be the full 16-bit lower half of that register. So clearly, since this is a smaller bit vector as a source than what it's moving into, it needs an instruction on what to do with the data it's not grabbing from AL. This is the instance when you want to consider whether you're going to use move Z to 0 fill those, or whether you want to use move S to fill it based off of the sign that did get moved in, whether you want to go ahead and sign extend with a 1 for a negative value or a 0 to represent a positive value. Okay, and these are just more slides. I kind of represent this. Now, one thing you should know is when we go ahead and do the signed extend, there's a instruction we can use, CLTQ, which is a compact way to sign extend from 32-bit to 64-bit values. So just an instance, if you wanted to go ahead and move those. So I have an example here. Well, here. So here, let me say, for instance, if we wanted to do this instruction here, a more compact and efficient way, instead of doing move sign with a your quad word, from EAX into RAX, so 32 bits, 64-bit, we can simply just do CLTQ. Just in case you see it, you know that's a move instruction. Okay, let's see here. But really, the big takeaways for this section is how do we move the data? Right, that's a big non-trivial task that our underlying system has to do. You should understand there's a lot of thought, there's a lot of consideration, there's entire operators where that is what their task is. And those operators, like any other operator, has a set of operands, and you should know what the valid forms of those are, especially since this is how we access all the data and write into all the data inside of our system. Okay, let's take a look at an actual example where we move data around. And let's look at an example, again, where we're not authoring the code because that's what you've learned to do in assembly, but how does this code get authored for us by the tools that we use, by things like GCC, to go ahead and convert into something that executes onto our system. So suppose that we have this code representation here, which does an exchange. And what do we do in this exchange? So it looks like this is returning. So just looking at the function signature here, we are returning a long data type. We have a name and identifier, a label for our function called exchange. And then we have two parameters. The first is going to be a pointer to a long data type, which we will call XP. And then the second is going to be the value of a long value. So inside of here, the first thing we're going to do is we're going to dereference that memory address to get the actual value that resides there into long X. Then we're going to grab Y, which is the memory address. And so what we're going to do is we're going to assign that to the memory address, or the value of what's that XP, and then we're going to go ahead and return X. So effectively what we're doing is we're taking the two values, putting one in temp value, and we're swapping them between locations. Let's see what that actually looks like when our system translates that into a series of moves in our assembly. So when we look at these parameters, the things you should know is what are the default registers that were responsible for handling parameters in higher level languages. So on exchange, we have two parameters, right? Our long pointer and our long value. So our XP identifier will go into our RDI register space. And our Y parameter will go into our RSI. So RDI represents effectively our destination index, and RSI represents our source index. Typically is, I think, the notional naming for that. So if we were to look at the label that we give to our function exchange, the set of operations that we should now be able to read based off of the way that these symbols are parsed is this is a memory lookup, right? Inside of our address mode, we have a set of parentheses. We will go ahead and then access RDI. And so we will fetch the value at RDI and then store that in RAX, right? Because this is our source and this is our destination. Then what we're going to do is we're going to go and take what's RSI. And so here, I'm actually going to have the value. It's not a memory lookup I have to do for this. It's going to be the actual value inside of RSI. And then I'm going to move that into memory that RDI is pointing to. And then we're going to return. So now we can see how high level code to do these kind of operations that read and write into all of our variables is actually working with these move operations at the very low level of assembly. And then this maps into our machine code. Now, RAX is typically used for storing your return values. So when you return something back from one function to another, understand that's usually where it gets deposited. Okay, so why is this worth talking about? Well, pointers in C are effectively just addresses in assembly, right? Probably by now you've already made that connection. Local variables like X are often stored in registers for faster access, and our parameters are passed through registers. between function calls. So this kind of starts to tether how these how a vertical stack of technologies are implementing to allow you to do what you do in like the world of Java, or in our case, in this class, the world of C. Okay, let's see here. The next thing we should talk about then is pushing and popping onto our stack data. So besides the set of registers and besides being able to access or move data between our memory and our register spaces and access or read at least the immediate values, we also have a lot of stat management at the assembly level to be able to store and recall data as our programs, as our applications process. So let's take a look at how the system's able to manage data that's not currently processed in this particular time frame. So we're going to look at push Q, we'll look at pop Q instructions to manipulate our program stack. And again, in case for any reason you forgot what a stack is, it's a data structure that exhibits the last in, first out discipline. So here we go. Yep. It's so as we add or remove, it's last in, first out, like a stack of pancakes. Our operations, your push adds data, your pop removes data. The top of the stack is going to be the end of the array where the data is added or removed from. Okay, so now that we got the very primitive concepts of a stack down, let's actually look at how our program stack operates inside of x86-64. So here we're going to have our memory region. This is going to be the program stack, which is stored in a specific memory region allocated to our application by the OS. So here we can see initially what's held in the respective registers that are designed to manage our stack. So you'll see we have, say, for instance, RAX, which we stated earlier is typically where our return values can be held at. We just have this value, hexadecimal value 1, 2, 3. We have our RDX, which is typically thought of as potentially our one of our general purpose stacks that we have, but that can also be like a kind of a destination stack of sorts. And then we have RSP, which is going to be our stack pointer, and that's going to let us know where the top of our stack is. So if we go ahead, holds the address at the top of the stack, and our growth direction is going to be downward, which means the top element has the lowest address. So let's see what that actually looks like in practice. So here, this concept is we are increasing addresses as we go up. So that means this is going to be the bottom of the stack, and this is going to be the top of the stack here. So at 108. So when we go one frame over, suppose we push RAX. So we have RAX. Suppose we do our push command, RAX onto the stack. Then the way that we update the stack based off of the contents of our register spaces that does all this administrative stuff is, well, our RAX is has the value 1, 2, 3. RDX still has the value of 0, but now notice that our stack pointer has advanced to hexadecimal 100. So now what we can see here that this was the former top of the stack an operation ago, in the prior operation, 108, but now it's going to be 100 because of the size of the data. We used a push Q, which is a quad word. So it's going to, so each one of these units, these hexadecimal units, that is our addressable space, represents 1 byte of addressable memory. That means we've advanced our stack pointer by 8 bytes. Or 8 units. Okay, so then suppose that we're going to go and pop that value from the stack. We saw how push serves as the location of, well, we pushed RAX onto the stack. So now when we pop RDX, we're going to overwrite whatever was in RDX. So RDX was empty. Now we're going to effectively put the value 1, 2, 3 in there. Well, we never overwrote RAX, so that's still also the value of 1, 2, 3, right? Hexadecimal. And now that we've popped that value from the stack, the pop operation is going to update the stack pointer to now have the top of the stack return to 108. So this, I mean, I'm assuming everyone, maybe it's not, like you could potentially be in this class without data structures, right? The requirements was 2120 and assembly. But this, like, stack management is definitely something you do in data structures. And it's something you do in 2120 as well, like talk about stacks. So everyone should be, and you did a lot of this. Did you do a lot of this inside of assembly as well? Like learn how to manage the stack and how the stack properties are all effectively just managed by register values that the CPU looks at when processing a set of directives. Okay. Perfect. So we've already talked about this example. And again, these examples are just pulled right off the book. So the syntax, as you could probably have guessed from the prior example, and I guess your experience working with assembly, is push is a operator. It uses one operand. In this instance, it's going to be a register value. And so, for instance, here, this operation that we can do, so the equivalent code of what push effectively allows us to do, because there's multiple ways we can move data around in our system, but this is an aliased way of doing these two operations, where you can go ahead and subtract this immediate value of 8, right, for the position of the address from your stack pointer. So we're subtracting our address by 8. And then we're going to move the value of RBP, the base pointer, by this to this value here, which is going to be the memory address here. So star RBP onto our stack, which is the value that we want to store when we go to do this right here, this RBP. So just showing how there's a way of calling our atomic level move operations to perform these tasks, like pushing and popping things off the stack. These are all just register spaces, and we can see how we're implementing operators from these simpler operators. Probably like what you realized you were doing, how in object-orientedness, you build complex sets of processing methods on top of your simpler primitive data types. And of course, pop is very similar. The syntax is just pop q, or whatever the amount of bytes that you want to go ahead, or your bit representation, and then some kind of register. And then that could as equivalently be this form of the move operation paired with an add, or an add operation as well. Now, one of the interesting things is, since we know that the stack can grow or it can shrink, right? It is like a contiguous block of memory that we kind of track based off of where the top of it is. It's possible to access an arbitrary stack position. The way that we can do that would be using the address mode that we had discussed earlier inside of this lecture. So recall that the syntax for this operation is this offset here, and then inside this parentheses, we can put our whatever the register is. So if we were to use this code here, our register being our stack pointer, we could then go ahead and put 8 in front of that, and that's going to act as an offset of 8 bytes. So that effectively then will get us 8 bytes above our current stack pointer. So just understanding how easy and how effective all of the management of the data is within the system, but how exploitable this potentially can be as well, right? Okay, let's move on. Okay, let's talk a little bit about arithmetic and logical operations. So most of these, just looking at this list, let me gauge the interest of the class based off of what you already have an expertise in. I'm assuming most of these you've already covered. You have load effective address, unary and binary operations, shift operations, and your special arithmetic operations. And again, these are pulled directly from the book. So I guess we'll go through, and if you haven't seen one before, stop me. Because I think a lot of these, this is probably what you spent a lot of time, if I had to wager my guess with, inside of assembly. So first and foremost is the LEA operator. It's short for load effective address. It's a very powerful instruction that provides a way to perform our arithmetic and addressing calculations. You could think of it as a variant of move Q. But the key difference is where move Q moves the content at a source address to a destination, load effective address just moves the address itself. So it allows you to load the effective address, hence the name. So it's primarily used for computing the address without actually having to dereference it. And its use cases in arithmetic calculations, pointer arithmetic, and address calculations. Pretty much things where you're using addresses for, right? Okay, so just a quick gander at load effective address. This is our set of operands for it. Here we have load effective address of RDX as a source or as our base, RDX as our index mode, as our index value, and then 4 would be our scale factor. So notice this is just using this address mode. So here shows you the details of how this might manifest, where load effective address, we give it a base, which is a register. We give it a index, which is a register, and then a scale factor. And this is all one parameter, which represents some location in memory, and then we give it some destination. So in this instance, the destination we're going to give it is going to be RAX. We know because it's just the percent sign. So what does this effectively do? Well, the effective address is, it's going to take that base, it's going to add it to the index, and it's going to multiply it by, and that index is going to be multiplied by the scale. So this, obviously, we do PINDAS, this does first, and then we do the addition. That's going to give us an effective memory address of this, right, in terms of this example. And so what we can think of that is being effectively the result of 5 times the value at RDX, and that's stored in RAX. So we can use our LEA operator for a pointer generation, for doing all sorts of memory tasks. So when we start thinking, how is things like maybe our pointers generated for us, this is effectively the underlying mechanism by which that can happen. So this example here, suppose you have an array starting at a memory location pointed at RDI, and we want to access the element 4 places. Then we could do the following instruction here. Oops, don't want to move that. Where we can load effective memory address without dereferencing. We pass the memory address at RDI and we offset it by the number of places that we want to do that. And that's going to be a total of 16 due to the size of the value itself in bytes. So like 4 bytes, 4 units at 4 bytes a unit is going to be 16 bytes that we want to offset. So to kind of piece this together, suppose I want to use LEA for arithmetic operations. Then let's take a look at this arithmetic example. Suppose RDX holds the numerical value of X, whatever X might be. Then the instruction using our load effective address using our address mode. So we would give it RDX as our base and RDX as the index, the same address. And then we'll give a scale factor of 4. We can kind of take advantage of how this function, how this operator works to perform an arithmetic operation. And then our immediate offset is 7. Well, the computation that gets performed from that is whatever value was held at X will get multiplied by 5, the scale factor, and then we would add the immediate value from our address mode 7, and then we could store that into RAX. So a clever little optimization trick where you're using effectively loading memory addresses to do mathematical, multiplicative, and addition operations. And again, one of the big things about this is we're not dereferencing memory to do lookups on this. And so why do I bring this up? This is just what compilers, these are clever uses that compilers might do to do computations. Why do I care about that? Well, again, the emphasis on this particular chapter isn't just to build a comprehension and an understanding of machine code and assembly code, but the machine code and assembly code that gets generated by software like a compiler. So when you go to disassemble this, if you go and look at this in a debugger and you're wondering, why is there an LEAQ when I'm doing a mathematical operation? This gives you an insight as to what the compiler might have done if it was toggled to a high optimization level, if that makes sense. Okay, let's see. Did y'all cover that? By the way, did y'all cover, was that something you covered inside of assembly as well, using load effective address? Oh, excellent. Okay, let me go a little quicker then. Okay, so there's 2 different kinds of operations, right? And this was true in Java as well whenever we talk about operators that are pretty common. You have your unary operations, which are 1 operand, and you have your binary operations, which are 2 operands. Let's take a look at the unary operations. This is going to be like if we wanted to go ahead and call increment or decrement. The words do exactly what you'd expect them to do. And also, just like you'd expect, since our data types are based off of how long the bit vectors are, we can always make it a inc or dec of a byte or a word, or a quad word, or an L, which is going to be our double words. So in this instance, we can go ahead and also notice inside of our address mode, we have put this in parentheses. That means that in this particular example, we're giving it a memory address that is held at our stack pointer. So it's a, hey, get the memory address of the stack pointer and increment it by 1. And this would decrement it by 1. Okay, let's take a look at our 2 operand. Typically, the 2 operands for our operations will have a source and a destination, as we stated earlier. So suppose, say, you have subtract and you have add, both of which we can specify how many bytes we want to add or subtract, and then we can give it, in this instance, in these examples, the sources are going to be register spaces. We know this because it's prefixed with a %sign, and the destination, which is going to be the second parameter, is also going to be a register space. So our 2 register spaces. Now, in these instances, it should be noted that this is the same as doing the compound assignment. So when we see subtract RAX and RDX, these 2 operands, I'm sorry, it's not just the source and destination, but these are going to overwrite. So these are going to take the 2 operands as input, and it's going to overwrite a value from this operation. And typically, we know that the operation that gets overridden on arithmetic operators is going to be our RAX register, our accumulator register. So we will take the value. So this will represent my X value. This will represent my Y value. And then I overwrite what was the value of RAX with the result of this subtraction or the result of this addition. So it's going to be like this compound assignment here and here. Okay, let's keep moving on. So you got to understand that the source destination ordering, we can read that as subtract RAX from RDX. So here, for the binary, then what we want to think of is really this value here that we're giving is the one that's getting overridden. That's the destination. Okay, some basic restrictions. I think we already talked about this, that for being able to move, we can take a register and we can move that into memory. We can take a memory and we can move that into a register. But one thing we can never do is move directly from one memory location to another memory location. Yep. Okay, let's keep moving on. Let's talk about our shift operations. And then we have our arithmetic shifts and our logical shifts. We've already seen this conceptually as it existed in C. This is just our mechanism to do these similar type of operations inside of assembly. And of course, it makes sense that these are assembly instructions and machine code instructions because one of the prime drivers that we try to facilitate with these languages is being able to move and operate in the form of binary sequences. So clearly, so much of what we need to do is shifting the values of bits on where they line up inside of our bit string, our binary string. So in this instance, this is also going to be a binary operand. We have our shift left. Here we can have, say, for instance, an immediate value, or we could also pass, if we wanted to, a register value or a value from memory. But this is effectively the number of bits we want to shift by. And then the second operand is going to be the bit vector in memory. In this instance, we're using an address of how we're actually going to shift that. So again, these are just mapping all the things we've already learned and how we're actually articulating that at the very low level system mechanisms for that based off of the set of commands that they give to us. And so this is just showing you the same thing. We're doing a shift. Yeah, we're shifting that left. And then we have our shift right as well. Now, when we shift right, recall that there's two different ways we can shift right. We can either shift right with an arithmetic shift, which is going to copy the sign bit, or you can shift using zero fill, which is your logical shift. So that's going to be in the value of SAR, SAR, or SHR. Okay, and similar principles. The first parameter is going to be the number of bits you want to shift. The second is going to be the register or the binary sequence that you want to shift on. You know, and then we also have the ability to have our, let's see, we have our arithmetic shift here. And so here we have our shift left, and we have an arithmetic shift left as well. But these perform exactly the same, right? These will just fill from the right with 0. Okay, let's go through. What else do we have? So we already talked about how we can shift right in detail. Let's move on. Okay, so this is where it's going to be relevant for Bomb Lab. Here, we're going to have a set of C code. And so this represents how our C code is then translated into this corresponding assembly code. So we can map how these operations manifest using these compiler optimization tricks we had discussed. So let's see what's happening here. Inside of this arithmetic function, we have an X, a Y, and a Z. And here, what we'll do is we're going to do we're going to take the long value, and it looks like we're going to do a XOR operation. We're going to do a multiplicative operation. We're going to do a bitwise operation, and then we're going to do a subtraction operation. And then finally, we're going to return whatever the value at T4 is. And here, what you can see that we're doing here is, in order to do this XOR, we can do an XOR right here. So the high-level XOR is using the XOR quad word as the operand to implement that part. And then this part here, this multiplicative property of take whatever our Z value is and multiply that by 48. Well, it's going to optimize that to be this load effective address operation. It's going to take RDX. And remember, our X, Y, and Z parameters are saved inside of RDI, RSI, and RDX in terms of what registers those are assigned to. So we're going to go ahead and grab the Z from RDX. And then we're going to use that as both the base and the index. And we're going to multiply that by 2, which is going to be the equivalent of 3 times Z. And then we're going to save that into RAX. Then here, on our sorry, I'm just looking at the 2 different values. Then on our next line here, where we have our T3, we would take T1 and AND it, so we can just call an AND between those. Oh, let's see. Oh, we got to finish that up. Sorry. So I get my Z here, and then we have one other address that's actually one other operation that then's going to go ahead and do that shift so that we can shift the values we need so that instead of 3 times Z, we're going to get 48 times Z. So you can see it's able to optimize that operation to do this arithmetic multiplicative operate. This multiplicative property is done in just 2 machine coding instructions or assembly instructions. Then here we're going to do the AND on our T3 value, just using an AND operand. And then finally, we're going to get our T2 minus T3. That's what's actually going to get returned. So we're going to subtract our RDI value, that's our X, from our RAX value, that's our accumulator that we had gotten from our last operation. And so that's going to put that into the register that we then have to return back from, which is going to be our RDI. Excellent. Does this make sense effectively? You see how you could take the high-level language and these instructions we talked about, how it optimizes and then translates it. But the trick is building up the ability to read these assembly instructions and knowing it maps to this representation high-level code, right? So it's one thing to say, oh yeah, I can take this high-level code and I can see how it gets translated, how it gets converted. But then when you're debugging, you want to be able to do the reverse. What are these set of operations likely doing if I were to remap it in a higher level language? That's why reverse engineering can be very challenging, right? You have to start, you only learn that very well by doing it and identifying the patterns that these compilers go ahead and use to perform these operations in. Okay, and this chart right here just shows you all the different operations that we have available to us, all of which you've probably already seen. So we have load effective address, we have increment, decrement, negate, not, add, subtract, multiply, integer multiply, XOR, or, and, our shift, our arithmetic shift left, our logical shift left, our arithmetic shift right, and our logical shift right. Care, don't care. Okay, so don't really care about 28-bit units. And here, let's just quickly talk about some of the special arithmetic operations. This represents our multiplier operation. So it's just a quick example of how this might work. suppose that we have RSI and RAX. This would be the equivalent of copying X to our RAX register. So RSI is typically where our parameters go, as you may recall. And then if we call multiply RDX, that's going to multiply our multiply by Y and then deposit that into the register space. And then in terms of division, we can see that we can either call signed division or unsigned division. So this would look like effectively this. We would move RDI. So let's just quickly take a look at our C code where given a division function call, and it looks like this, hang on, let me, there we go. Oh no, whoops. My parentheses has gone, there we go. Oh, well. Well, you can see that's a parentheses. Anyway, I have my X, my Y, and I have 2 pointers. So what I'm going to do is I'm going to compute my quotient, which is going to be X divided by Y. I'm going to calculate my remainder. That's going to be my X modulus Y. Notice these are integral values. That means it's not floating point values. Then I'm going to take my quotient and I'm going to use the memory address that's provided to me here and store that value at that memory address. And then I'll take my remainder and store my remainder at my remainder pointer address here. So what this would actually look like inside of our code here is we would move our RDI value. So that's going to move our X to the lower 8 bytes of the dividend using, and this is going to signed extend, and it's hard to see. I think I lost an operation here to the upper 8 bytes of the dividend, and then we can call our division operation on RSI. And I think I had actually lost some operations in this example. So I will fix this slide so you can see the rest of the operations that actually occur. That's what I was looking for. Okay, so those are our operations. Let's quickly now move on to how we go ahead and define our control. A lot of the control inside of these lower level applications are done with labels and jumps. So the key terms that you're really going to want to look at are going to be these here. That's going to allow us to understand our condition code registers. And we'll take a look at these for conditional branching right now. So our CF represents our carry flag, our ZF represents our 0 flag, our SF represents our sign flag, and our OF represents our overflow flag. So these are all just single bit registers that store attributes of our arithmetic and logical operations from the system that the system would have to be aware of when it goes to do the next set of operations, or how to go ahead and parse the results of a computation that just got executed. And so these are just instances where we can go ahead and understand whether there was a overflow, or whether the 0 flag was set, whether a negative flag was set, or whether our signed overflow. These are mathematical conditions that we can take and look at given some t, which is the result of, say, for instance, a arithmetic operation of a plus b. So one big thing that you should know is that load effective address, increment, and decrement do not touch any of your condition flags. So other operations like add and subtract do, but you'll never affect those with these particular operations. So understand that that's a thing. You can't overflow or 0 flag. You can't cause those to trigger with these operations. And load effective memory address doesn't cause any conditions to trigger. Our compare instruction sets the condition codes based on the differences between 2 operands. So now let's start looking at how we can use operations designed for control. This is obviously equality operations when we're comparing one operand to another. And so the only difference between compare and test is that if test is negative, 0 or positive, we can go ahead and use that. And I'm pretty sure test doesn't trigger your carry flags either. Okay, let's move on. We have the set instruction, which alters a single byte to 0 or 1 based off of the condition codes. So this just lets us set based off of certain parameters, like we can go ahead and have set Z that's going to set to 0, set not 0, or that's like our not equal versus our equal. This is going to NLE is going to be greater than. NL is going to be greater or equal than. Not greater than or equal, that's going to be less. Not greater is going to be less than or equal to. So clearly you can just see how our instructions are defined right here for all of our relational operations, which is super important when we want to start creating these labels. This represents a label. And then we can do a compare of A and B. And then based off of this comparison, we're going to be able to go ahead and implement some kind of logic on top of that. So it's going to set our values in our register and then move from one address to another, or clear the rest of the EAX. Okay. Signed versus unsigned, jumps. Okay, this is where it gets interesting. This is where we can start jumping to memory addresses, and we can give these labels to be able to jump. Typically, we prefix our labels with a period. Yeah, and so these are just various examples that we can then go ahead and use jumps. So this is what you'll probably see the most is we have the standard jump where you give it a label, or you can go ahead and do an indirect jump given some operand like a memory address. So you can either give it an immediate memory address or you can give it a label that's defined somewhere in your code base that it jumps to. And then the rest of these just use labels. So only jump can you use the operand from where you can use indirect jumping. But the rest of these are going to be jump if equal, jump if not equal, jump if negative signed, jump if not signed, so that's non-negative, jump if greater and equal, jump if less than and equal, jump if above some value, jump if above or equal to some value, jump if below, or jump if below or equal. So obviously one represents like logical data, the other is like the arithmetic data, signed versus unsigned. Everyone's used these, right? Perfect. Okay. This is just representations of indirect jumps. This illustrates JMP is the only one that allows us to use non-labels. So this is an instance of where we can go ahead and give a jump target based off of some memory address or some register address. So notice if we jump to an address that's used inside of a register space, we can actually prefix it with a star, the same we would do almost in C with dereferencing. But normally just use labels, but now when you look at machine created assembly, if you see jump commands and not like JNEs and whatnot, you now know how to track where it's jumping to. Yeah, okay, example of relative addressing. So one of the powerful things, so this is program counter relative addressing. Do I have time to talk about this? We'll probably talk more about this example. Do I want to talk about this? Is it meaningful? Oh, how much more time? Yeah, okay, so we have a little bit more slides. We might finish up with some of the looping, or I might just jump next class to the bomb lab. I think a lot of this stuff y'all are familiar with, right? Yeah, well, I'll post the slides up. Really what looks like the rest of these slides are dealing with is how we can go ahead and manifest our looping logic and our selection logic using the sets of jumps and comparisons to be able to use our consecutive execution of assembly code to be able to now implement the forms of if else, or loops, being able to jump back and then evaluate until we exit out of our loop. And I'm assuming you had lots of practice with that last lecture. I mean, last semester. So I don't want to bore you with content that you already know. So if you want, you can review the rest of these slides. I don't see anything that's super interesting that you probably haven't seen already. So I don't see the need. Yeah, switch statements, loop statements, procedures, passing data. Is everyone familiar with the runtime stack? Did you cover this in any great detail inside of assembly and how your runtime stack holds your various sets of arguments and your saved register? You can have your saved registers, your local variables, and then you can go ahead and populate your stack with multiple sets of values, and then you can extract them at any time. Okay, perfect. So y'all have covered this concept as well. Okay, perfect. Control transfer, and then of course, you use your runtime stack because you're pushing your sets of function calls onto the stack. You execute the sets of instructions. You have your memory inside of the stack as well that then gets cleared off as the function and all of its associated local variables gets processed. And then you jump back to the next function that's on the stack. So the control transfer between functions, the way that data is passed from one stack frame to the next and then returned from one stack to the next is all something that everyone feels comfortable with. Yes, no? Oh, I guess the question is, do y'all want me to lecture about that, or do we just want to go into the bomb lab next class? How are y'all feeling about how assembly interfaces? I guess, like, do you feel like you are comfortable with that, the concepts with that? You want to mull over it for a little bit and we can make this decision on Monday? Okay, I'll do that. Look over the slides I haven't covered yet, and then we'll decide whether it's worth having deeper examinations into it. Because it's important that you understand what's happening. The reason why it's important, and the reason that I want you to reflect on this then is I want to have the assurance that you understand how we took all this theoretical concepts mathematically of representing our data, regardless of what that data is, as binary representations, and then mapping the transformation of those binary representations using all these operations, how we can then implement that, how we can actualize that at the assembly level. Because once that theory has been actualized in practice at the very low level system level, all of our high level code gets mapped to those low level representations, which then function at that pure mathematical kind of conceptualization that we've defined earlier. And that way we are mapping to the physical these concepts that exist in a theoretical space, but in a very practical and applicable way. So like there's a lot of advanced concepts like how are we calling multiple functions? How are functions being nested together so they can rely on each other and share data between each other and then process to some desired solution? Because we're building very complex software systems off of very simple atomic elements. So it's very important for you if you're really tasked with being an expert in the domain of computer science, how these very atomic concepts are build these very complex binary like computer systems, how we create these very complex architectures from something that pipes down into something that's very simple. So look over this. I pretty much assume that you might have seen this, but I want to make sure my assumption is right. And the best person or the best people to ascertain that would be all of you, because you literally just took this last semester. So if you don't feel comfortable with one of these concepts with the, because I do think that this is a pretty important concept, how the runtime stack works because a lot of what the system has to manage is this. And this is a non-trivial concept. So look over the slides, and if you have any questions, we'll address those on Monday. And if not, we'll start with our bomb lab.
Is there, so last class I was asking about, turning in the data lab. 'cause
Oh, yeah,